Hi, welcome to the 10th lecture of EC 113, Communication Electronics. In this lecture, we will be talking about network analysis. So where are we so far in this course? We've talked about the systems level approach in designing and analyzing our communication blocks. We know how the communication blocks interact with each other, what is the purpose of each communication block. We also did link budget analysis. How does noise affect our circuit? How does distortion propagate in the circuit? So on and so forth. We've also looked at how we create selectivity and bandwidth in the circuit by designing resonant circuits and filters. And we also talked about how to design mixers to create or upconvert and downconvert our circuit and transmit them through an antenna. Okay? So the system level approach deals with determining how much power we need to transmit over the free space or over the channel. Okay. Uh, Resonant circuits are used to create selectivity and so on and so forth. And if we're talking about, well, our design approach so far is we treat these blocks as separate and then design away. So your source block is separate from your modulator block. Your modulator is separate from your amplifier. Okay, and so on and so forth. The problem with that is in system level view, there is a loading effect between different blocks in your circuit. The output impedance here could be affecting the input impedance here. Okay? The output impedance here could be affecting the input impedance here. And the performance between your blocks could be suboptimal. Okay? So it's not easy predicting the problems when you're looking at it in a system level view. But if you look at it in a circuit level view, you can see the problems. However, it becomes a little difficult to analyze the whole system because the circuit of the source is already complicated in and of itself. The circuit for the modulator is already complicated. If we connect those two together, it will be difficult to analyze them. So instead of looking at it in a system level view and a circuit level view, we can think of them as networks. Okay? And networks bridge the gap between your system level analysis and your circuit level analysis. So each block in your system can be considered as a network of circuits with defined parameters that will interact with the network parameters of the next block. Right? So before we go there, another reason why we're talking about networks is because of uh, the frequency that is being used in communication electronics or communication systems is very high. So how does the high frequency come into play when we're talking about networks? Okay, so you're familiar at circuits with low frequencies. Let's say you have a circuit operating at 100 kilohertz. So at 100 kilohertz, let's say you have an RC circuit right here. Here you go. For 100 kilohertz, the wavelength of the wavelength of this, if you're talking about an electromagnetic wave operating at the speed of light, of course, the wavelength is around 3 kilometers. That would mean that the traveling wave from this source up to this point right here is actually has a very large wavelength. So that would mean that the voltage and current here is just the same or approximately equal to the voltage and current here. Because since your wavelength is 3 kilometers and your circuits are normally less than a meter, the changes in voltages in terms of space, okay, is insignificant. That's why you can approximate the voltage here to be equal to the voltage at this point. In high frequencies, let's say if you're operating at 1 gigahertz, the wavelength is 30 centimeters. It's the length of the circuit is already significant compared to the wavelength of your uh, electromagnetic wave. So if you look at again the same circuit from your RC circuit, if you look at the same circuit right here, the voltage here could be different, could be, it's clearly different from the voltage here. And if you want to complete the circuit analysis, you need to be able to use Maxwell's equations to factor in the different spatial effects of the circuit. So it becomes difficult to analyze the circuit. That's why it's more convenient to express the circuits as networks. So by expressing them as networks, we convert the complications of using Maxwell's equations, convert them into networks, and simplify the analysis of our circuit networks. Right? So this is how we do it. We have, for every block, we have an n-port network. We generalize it to have n, an integer number of ports. So the ports are where the voltage and current are measured and are extracted. So at these ports, you can connect different blocks. You can connect different blocks on these ports and see how these different blocks interact with each other. So because of having n ports, we will describe the different parameters at each port and how they interact with each other. It results into a matrix equation. So this is a visualization of your n-port network. If you have a high frequency input, you can think of the voltage as a traveling wave going inside, okay, going inside your network. So you have traveling waves going inside the network from different ports, from different sources in your network. Right? The tendency of these traveling waves is that when they enter the network, they will be scattered around at different exit points defined in your network, right here. Something like this. Okay? And it could be reflected back towards the port of origin. Right? So that is what happens inside an n-port network. So if you have an excitation from one port, it could be scattered around to different exits of your network, something like this, and it could be reflected around like this. Okay? So the parameters that we are going to track in our n-port circuits or n-port networks is the voltage, which is the sum of the voltage going in and the voltage going out, and the current, which is the difference or the difference between the current going in minus the current going out. Okay? The easiest set of parameters to define is the impedance matrix. So the impedance matrix is defined by this equation. So if we let the voltages at each port, measure them, and put them on a column matrix, it becomes a vector. It becomes a vector, okay, a column vector. Your current also becomes a column vector, and the parameter that is relating them is the Z matrix. So in effect, the voltage becomes Z times I, which is Ohm's law. So this is Ohm's law in the general case when you have n ports. Your diagonal terms correspond to the input impedance at different ports, and the off-diagonal terms correspond to the interaction between your two different ports. Okay? So how does it work? If you have a current injected at port 1, it will create a voltage at that same port, and it will also create a voltage at port 2 to port N due to these off-diagonal terms right here. Okay? So to solve for the Z parameters, you need to be able to inject a current at port J and measure the voltage at port I. So this will be the input and this will be the output. Right? If we drive port J with current IJ and all others will be open circuited, that would force the current at each of the other ports that is not port J to be 0 since it's an open circuit, and then you measure the voltage at the different ports. You'll be able to measure the different parameters Zij. We also call this the open circuit impedance parameters since all the other ports are terminated by open circuits to force the current to be 0 on all the other ports. And then you drive port J by a current I. Right. A dual of the Z parameters are the Y parameters. It's the admittance matrix. Okay. So it represents the currents as outputs and the voltages as inputs. And this is actually widely used for transistors. Right? So if you have a voltage input at port V1, it creates a current at the output at port 1, port 2, and so on and so forth. In matrix notation, it's equal to this, and it's still the same, it's just Ohm's law. But in this case, you're talking about the admittance of your network. To solve for the individual elements of the admittance matrix, you just force the voltages at each of the other ports that is not port J to be 0, and that is a short circuit. Right? If you put a short circuit at each port and then drive the voltage at port J with voltage V, currents can be measured at different points, at different ports of the circuit, and you can solve for Yij by dividing the output current with the input voltage. So this is the short circuit admittance parameters of your N-port network. Okay? And we can actually relate the Y and Z parameters with each other. Generally, they are complex, as you already know from the definition of impedance and admittance. The Y and Z parameters are actually inverse matrices of each other, as you can see here. So the admittance matrix is equal to the inverse, this is matrix inverse of the Z parameters. Right? So your N-port network, you have N squared independent quantities inside the matrix right here. So we can look at some different cases, some special cases for your networks. A reciprocal network is a device that does not contain any non-reciprocal media. So what does that even mean? Right, so let me simplify that for you. Reciprocal networks, what does that mean? If you have an N-port network, right here, any input here will create an input here, 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 okay? And let's just change the color. If you have an input here, the same effect will be the output here. So it reciprocates the effect when you have an input here. It reciprocates the effect of this input. So the input here reciprocates the effect of this input. Right? That's what it means when we talk about reciprocal network. This results in a symmetric matrix. Right? That means your off-diagonal terms will be equal to the corresponding same subscripts right here. Right? So if you flip the subscripts, they are equal. This is a symmetric matrix. Right? Now, for a lossless network, well, that just means that the elements inside the lossless network does not introduce loss. So what element has a lossy component to it? It's lossy if you have a real part in your impedance matrix. So if you have a lossless network, you'll have a purely imaginary matrix. So this is a special case. Okay. So now, let's define what we call the reflection coefficient. You have seen this in filter design. Let's formalize it. The reflection coefficient relates the incident electric field, which is the electric field going inside your network, and the reflected electric field, reflected voltage rather, and the reflection coefficient is equal to this, which is equal to this, where ZL is the load impedance and Z0 is the characteristic impedance. What is the characteristic impedance? Right. So the characteristic impedance is defined as federal standard to be this. Okay? So don't be afraid. It just means that it's the impedance that when you have a transmission line. So if you have a transmission line, okay, and it's terminated by some characteristic impedance, okay, it's terminated by an impedance equal to the characteristic impedance. I apologize about that. Let me try to draw it again. So you have a transmission line right here. Oops. Let's just put wires on it. And we have a transmission line and terminated by an impedance that is equal to the characteristic impedance of the line. That just means that any input voltage going inside here won't have any reflected voltage. So there will be no reflections at the standard, or at the rather at the impedance. So that is the characteristic impedance of the line. That's just it. So you don't need to be afraid of this definition by the federal standard. Right. Right. So that is your characteristic impedance. Right. So your scattering parameters, so you just ignore this slide. Your scattering parameters is a type of endpoint parameters that deals with the scattering of the voltage waves and current waves inside the network. Okay? So if when we were talking about Y and Z parameters, we look at current and voltages as the inputs. For S parameters, by scattering parameters, we're talking about how a voltage wave going inside the endpoint network is being scattered around the network. So I provided a visualization of this earlier in your endpoint network. When you have an input voltage going inside your endpoint network, it will be scattered around. Okay? And this provides a complete description of the network seen at its endports. And it also unifies the high frequency behavior and simplifies the high frequency behavior of an endpoint network, okay, with respect to terminal planes. Anyway, so the analogy of it is with light is if you have an incident electric field going into another medium from medium 1, what happens at the boundary between medium 1 and medium 2 is that a wave will be reflected back and some of it will be transmitted. Okay? So this happens in light. When you have a lens, or let's say glass, you have an electric field incident to that glass, some of it will be reflected back. That's why when you look through a glass, you'll see a part of, some of it will be your reflection, and the others will be transmitted, and that's what you see on the other side of a transparent glass. Okay? So at high frequencies, this is actually the best way to represent your endpoint network because it deals with a voltage wave going inside the network and the voltage wave going out of the network. Right. So this is your endpoint network. Again, any input going inside will be scattered around at the different exits of your endpoint network. And it could also go back to where it came from. That is your S parameters. And it relates the voltage going out and the voltage going in. Right? So in matrix form, the vector of the voltages going out is equal to the S parameters multiplied to the voltage going in. So this is your incident, so that one, and this is your reflected, that one. Okay? So to solve for individual S parameters, you need to be able to force any input, okay? You need to be able to force the input wave from different sources to be zero. Okay? So basically, if you have an input here at this port, there shouldn't be any other inputs. You need to force the other inputs from the other ports to be zero. So this will be cancelled, 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 and cancelled. So you'll be able to measure the wave going out here, plus the wave going out here, plus the wave going out here, and the wave going out here, and the wave going out here. And to force them to be zero, you need to match that part. So this is zero if all the other ports are matched by the characteristic impedance Z0. Okay? So just to summarize what we talked about, to be able to measure the Z parameters, you need to open all the other ports. Y parameters, you need to short the other ports. And for the S parameters, you need to match the other ports. That's it. We also define the definition of a reciprocal network and a lossless network, the reflection coefficient, which is a generalization, a special case rather of S parameters. We generalize the reflection coefficient into S parameters, and the S parameters, you need to specify the characteristic impedance of your S parameters. So what better way to visualize that or to know more about that by using an example. So find the S parameters of the circuit below, and let's say the characteristic impedance is 50 ohms. Okay? If it's 50 ohms, then to solve for S11, we need to match this port 2 by 50 ohms. That would mean that there will be no reflection going back from this port. Okay? This port will have no reflection. So to solve for S11, we need to get the reflected voltage wave when you have an output right here. When you have an input right here, what is the reflected voltage wave? So first, when you put a 50 ohm resistor here, solve for the equivalent resistance seen at port 1. Once you solve for the equivalent resistance, it turns out it is 50 ohms. The reflection coefficient can be solved by this equation right here. So the input impedance is the impedance seen at port 1. So that's Zin minus Z0. Z0 will be your characteristic impedance. So solve for that. Turns out that the S11 of this circuit is 0. Right? If we match port 1 and solve for S22, you'll get the same reaction since this circuit is symmetric. And that means it's a reciprocal circuit. Then your S22 is equal to S11 is equal to 0. Next is if you have an S21. Solve for S21. You need to get the voltage at the output right here. Why are we getting the voltage here? Recall that the voltage at the second port is equal to the voltage going in, V2 plus the voltage going out. Since we force this to be 0, then the voltage across this resistor is basically the voltage of the voltage going out of the circuit. Okay? So, if we try to solve for S21 here, that's just nodal analysis. Just get the voltage here. Okay? And to solve for that, well, turns out that your V2 minus, just get the voltage here through nodal analysis or any other circuit analysis techniques, the S21 is equal to 0.707. And if you put it in the reverse direction due to symmetry of the circuit, that's equal to S12. So to consolidate everything, your S parameters is equal to this. If you have a voltage input here, the voltage going out is attenuated by a factor of 0.707. So it's multiplied by a factor of 0.707. If you get the decibel equivalent of that, turns out that the network is a 3 dB attenuator. So it's 3 dB since the power going inside is halved when it goes out. Okay. So some special properties for a reciprocal network, since if you have something like this, it's symmetric, basically your S matrix is equal to the transpose of the matrix. Okay? So what does that mean? It just means that it's just the same condition as your Z and Y matrices, where Sij is equal to Sji. Okay? Now, for a lossless network, okay, basically it satisfies this. S multiplied by the Hermitian of S is equal to your H matrix or your I matrix, which is the identity matrix. It just means that it's a diagonal matrix with all the diagonals equal to 1. Okay? For a lossless network, you satisfy this equation. Okay? H here pertains to the Hermitian of S, or the conjugate transpose. You transpose the matrix and you complement each of the terms. Okay? So let's have another example. So find the S parameters of the circuit below, the characteristic impedance of 50 ohms. Okay? So for this, well, if you look at the circuit, it's symmetric. So if you look at port 1, it's the same reaction to port 3 and port 2. Okay? Since the circuit is symmetric. So you only need to solve for 2 S parameters, and you'll be able to solve the S parameters of the different ports, since it's a symmetric matrix. Okay? So you only need to solve 2 S parameters and you'll get these S parameters right here. So what will happen? So you match 1 by a 50 ohm load. So this is 50 ohms. And analyze this as if it's a 2-port network. You'll get an S11 and S22, and that is equal to S33, and S12, which is, since it's reciprocal, it's equal to S21, which is, since again it's symmetric with all the ports, that is equal to S13, which is equal to S31, and so on and so forth. You'll get this result for your S parameters. If you have an input at port 1, it will be divided evenly to ports 2 and 3. So if you have an input here, it will be divided evenly to ports 2 and ports 3. Okay? So this is basically a power splitter, where you have equal power split into 2. You have your power here split into 2 right there. Okay? So actually, if you get the total power at the output of the 2 outputs and compare it to the power of the input, you'll actually see that you have some form of loss inside absorbed by the 3 resistors right here. That is because the total power at the output is actually not equal to the total power at the input. Okay? So this is our 3-port parameters. So just a special property. For a 3-port parameters, the rows and columns always add up to unity for S parameters and 0 for Y parameters. So that is generally true for simple networks, with some exceptions. Your Wilkinson power divider, and I don't need to know all the details here. Anyway, so an example of your 3-port Y parameters would be, again, I already told you this, it's widely used for transistors. If we let port 1 be the emitter, port 2 be the collector, and port 3 be the base for a bipolar junction transistor, then we can actually separate the Y parameters at each ports, right here. Okay? For different configurations. For a common emitter, you just need this part of the Y matrix. Common base, you just need this part of the Y matrix. And for common collector, you just need this part of your Y matrix. Okay. So let's look at then let's look at two-port networks. It's a special case of n-port networks. Okay. And most of our RF networks are cascaded two-port networks. Okay. And other network representations that only apply for two-port networks is your transmission parameters or ABCD parameters. Okay. So how does this ABCD parameter work? Consider this network right here with ABCD parameters. It's a two-port network. There's a voltage input and a current input, which results into a current going out in this direction and a voltage with this polarity. Just note first that the current is at port 2 is going out of the port. Okay? As opposed to what we define for Z and Y matrices, the current is going into the port. So be careful with that. For a two-port network, the ABCD parameters is that the current here is going into, or going out rather, at port 2. The convenience of this is that when we connect it with another network with its own ABCD parameters. So if we connect it with its own ABCD parameters, then the current is already going inside this next network right here. And we can just cascade these two networks by multiplying their ABCD parameters together. Okay? So the ABCD parameters are defined as this. Okay? So if we have V2 and I2 at the input and V1, I1 at the output, makes it easy if we cascade matrices. If we have V1 and I1 at here, V2 and I2 here, V3 and I3 here, then V1, I1 is related to V2, I2 by the ABCD parameters of this matrix. V2, I2 here is related to the V3, I3 here by the ABCD parameters of this network right here. Okay? Combining the two matrix equations, we can now relate V1, I1, which is the input, and V3, I3, which is the output, by multiplying the two matrices of your ABCD parameters. Okay? So this is just matrix multiplication, you'll get this. So if you extend that to more, you'll get a larger matrix multiplication right here. So an example, let's say you have a series resistor. So series impedance element Z. To solve for the ABCD parameters rather, first we need to get, this is the voltage gain. To get the voltage gain, your output must be terminated by an open circuit. So that would mean I2 here will be 0. So if I2 is 0, then we can now solve for V1 over V2. Since there's no current here, then there's no voltage drop in your impedance. Therefore, V1 is equal to V2, which makes A equal to 1. Okay. Solve for B, it's V1 over I2. So we will then get the short circuit current here. So take the short circuit. The current here is just the voltage input divided by the impedance Z. Okay? So substitute that, you get the current, and divide that, you'll get B equals Z right here. Okay. Now let's have a current input I1. Okay. Have a current input I1 and let's say we have an open circuit right here. We can't have a current here since you have an open circuit right here. Since that is open circuit, we must force the current here to be 0. Okay? So, since the current here is forced to be 0, you have a voltage here, then the definition of C, which is I1 over V2, that will be equal to 0 right here. And finally, for the current gain, take the short circuit right here, solve for the current. The current here is equal to the current here, then your D parameter is equal to 1. So for a series impedance Z, the ABCD parameters is equal to this matrix right here. Other configurations can also be derived. Let's say you have a shunt admittance Y, the ABCD parameters become this equation right here. Let's say you have an n:1 transformer. The ABCD parameter is equal to this one. So just an exercise. Okay, so derive the ABCD parameters of a pi network illustrated below. The answer is, for this, you need to define an ABCD parameter first. So the ABCD parameters is equal to 1. The admittance of this is 1 over Z3. Okay? Then this one is 0 and this one is 1. So this is the Z parameters of this. The Z parameters of Z1 is 1, 1, 1 over Z1 right here, and 0. And finally, the Z parameters of Z2 is 1, 1, 0 right here, and you have Z2 for your B parameter. And you multiply this matrix by this matrix by this matrix. Okay? And you do that, you'll get the total Z parameters to be equal to this equation right here. Okay? And you can verify that by analyzing the ABCD parameters of this whole matrix right here. So to solve for A, you need to maintain this open circuit and solve for V2. So you have a V1 right here, solve for V2. Okay? So V1 right here is divided into this voltage here and here. So these two impedance divides this voltage. Okay? So you get a value for V2. And take the ratio of V1 divided by V2. Take note, it's V1 divided by V2. You'll get this A parameter for your circuit. Excuse me. Okay? So that's your ABCD parameters. So how does this relate? How do we apply the other parameters then? If our other parameters cannot be cascaded, how do we analyze circuits better? That's because you can actually convert your S parameters or your high frequency parameters into ABCD parameters. It is actually possible to convert them from one another. As you can see, Z was related to Y by an inverse transformation. So your Z is equal to your admittance matrix inversed. So to convert it, you just need to inverse it back. Okay? So what prevents us from converting your S parameters to Z to Y and your S parameters to A, B, C, D and vice versa? It's actually possible to convert them. And this is the formula for that. Okay? So the S parameters and ABCD parameters are related this way. Okay? And your S parameters and ABCD parameters are converted in this way. Okay? So that is your conversion. And by converting them, you'll be able to simplify your analysis. So if you want to get the total S parameters, say of this network, if you want to get the total S parameters of this network, first you need to get its ABCD parameters, cascade them, get the total ABCD parameters, then convert these ABCD parameters back through this equation and you'll get the total S parameters. Okay? So most of these high-frequency circuits are expressed in terms of their S parameters, since S parameters are actually the easiest parameters to measure in terms of frequency. Okay? And a lot of these complex circuit networks can be considered as cascaded two-port networks. And if you convert these S parameters to ABCD and then cascade them, multiply the matrices, the ABCD matrices, and then convert them back, makes it easier for you to analyze the circuit. Okay? So that is the end of this lecture. So if you want to look at the other conversion, so from ABCD to Z parameters, ABCD to Y parameters, and vice versa, they are in the books. So you can just consult the books for that. And this is the references. That's the end of this lecture. If you have any questions or comments, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting. Bye-bye.